Hello and welcome to this video which is entitled C4.1 What are standing waves? Now the syllabus reference there and the outcomes that you can see on the screen come from the IB Physics syllabus. This is an SL topic. However, this video is suitable for anyone who's just sort of starting out to learn about standing waves or stationary waves as they may be called in an alternative syllabus. So do feel free to take a look even if you're not studying IB. Ideally, you should be taking notes during this time, so make sure you have a pen, paper, whatever you need to take some notes. If you're one of my students, you might have a structure strip beside you to make sure that you're guided on those notes so that you're not just copying down what's on the screen, but more taking something in a structured way. So feel free to pause the video at any point, including now, just have a look at those outcomes. And if we're ready to go, let's get learning about what standing waves are. Now, waves as a topic should be something familiar to you. If you're asked to give examples of waves, you might talk about water waves, light waves, or sound waves. Light being an example of a transverse wave, and sound being an example of a longitudinal wave. Now, those are very familiar topics. You might even learn them at earlier year groups. However, you probably have studied standing waves until now. Now, in order to really understand what we mean by a standing wave, it's important to understand what we meant by those examples I've just given. Those are all waves which we would describe as progressive. And a progressive wave is simply a wave which takes energy from place to place. So I'm speaking to you right now. There is a progressive sound wave going from my voice to your ears, essentially, via the computer. Okay, so a progressive wave transfers energy. It therefore has a direction, a velocity, a speed, and you can have the idea of a moving wave going from A to B. Now, we need to have this definition down because standing wave is kind of a counterpoint to this. A standing wave is an oscillation which has zero speed and therefore doesn't transfer energy. In other words, it's an oscillation which doesn't move from A to B. And again, I think the first time students learn this, it's quite counterintuitive. It's quite confusing what we mean by that. And that's really my aim of this video, is to make sure you have an idea of what a standing wave is. And then later when we can see how these apply to certain situations. So to kind of illustrate this further, I'm going to show you this GIF. And I really like this one because it has an excellent demonstration of the difference between progressive and standing waves. Now, at this point, you could take a second to think which one of these is progressive and which one of these waves is standing. And hopefully find that most people would say the orange wave is a progressive wave. You can see that progressive wave is moving from left to right. It has a frequency, a wavelength, an amplitude, etc. And it is therefore, it should be familiar to the kind of waves that you've studied before. This could be a light wave, a water wave, a sound wave, etc. Now you might actually not realize it, but there's another progressive wave on the screen here. It's a lot lighter. It's this gray profile which is going left, and it's kind of identical to that orange wave. However, it's moving in the opposite direction. So actually there's two progressive waves on the screen. Now the final one, which we've not discussed, is the purple wave, and hopefully you can realize that this is a standing wave. Again, it has a frequency. It has a wavelength. You could think about amplitude here. You could talk about crests and troughs, etc. But notice that it is not moving. There's no direction of motion here. In other words, our wave is standing still in that direction relative to the other waves which are moving. So this is what a standing wave might look like. And again, in a future video, we'll be talking about the form of standing waves and the different shapes that they can take under certain conditions. Now, the reason I really like this GIF is because actually this GIF is showing how we make a standing wave. The standing wave in this video, the purple one, is actually the resultant of the two progressive waves. So we've got the orange wave and the grey wave who are superimposing, and they are adding together, if you like, according to the principle of superposition, to make this purple wave. So when we want to make a standing wave, what we do is we need two identical progressive waves, and they are going to superimpose on each other. Okay, now those two waves, as you can see in the video, must be traveling in opposite directions. They've got to be coherent. They've got the same frequency and have constant phase difference. So you notice that because they've got the same frequency and, I should say, the same speed, but are moving in opposite directions, that is what allows us to form this standing wave. So it's not very easy to form a standing wave. Okay, it's not something that you'll see a lot. However, if we're able to make these specific conditions, meet these specific conditions, we are able to form a standing wave just by adding two waves traveling in the opposite direction to each other together. Now, how do we achieve that? One way of doing this is through reflection. You could imagine you've got your orange wave moving to the right and meeting a boundary at this side here, and then reflecting as that light coloured wave. And what you'd find, we often do this with microwaves, experiments you can do when you reflect microwaves back on themselves. The two waves interfere with each other and form a standing wave. So that's just the basics of kind of standing waves and what they are, how they are formed. As I've said before, it might be an idea right now to pause, add to your notes, make sure you've got these concepts down, because what we're going to do is talk about some of the features of a standing wave and focus on a few ideas of amplitude, of frequency, and of phase, which are really important as you progress through the course. So feel free to pause now, otherwise we'll get moving on to the next slide. Okay, now that we've thought about sort of how we might make a standing wave and the distinction between standing and progressive waves, let's look at a few features of a standing wave, and these are going to be common throughout the next couple of units that you study. So I'm going to show you this picture just now. Now, this is a very commonly kind of found picture of a standing wave. There's a couple here, and we'll talk about the differences between them. And I often find that students get confused as to what they're really looking at here. So I think it's worth just taking time to break this down. Let's look at the top image here, because this is probably the image which might be the most familiar to you. If you've ever played a guitar or any other string instrument, you'll have seen this kind of pattern. If you imagine we pull the guitar string up and then let it go, it will oscillate up and down in this case. It has two fixed ends, more on that later, and the oscillation is anywhere between these points. So you notice here we've got this bold line at the top. You can imagine this is perhaps the current position of the guitar string, and then at a later time it's going to be slightly further down, slightly further down, slightly further down, and more, and it's going to oscillate between these points. So these dashed lines indicate the potential positions of, say, a guitar string throughout the oscillation. Now, the reason I use a guitar string is because the guitar string is actually a really good example of where we form standing waves. And it's one which you guys should be familiar with. And actually, standing waves are really important to many instruments, which we'll talk about in the next section. Now, you may never have seen a guitar string in this form, but however, it's actually possible for this to happen. A guitar can take a standing wave, which takes this shape. You notice we have a positive displacement on the left and a negative displacement on the right. And what would happen there is this left-hand side would move down and the right-hand side would move up. And again, those dashed lines show the shape of the string at different time steps. Again, this is going to be something which will come up later. These two pictures are different standing waves which are forming on the same string, and there are certain conditions at which these be met. And hopefully this top image is the most familiar to you. Now, regardless of which of the waves you're looking at, we find that within each of these images, if you like, within each of the standing waves, all of the points oscillate with the same frequency. There's a time period and they have the same frequency, however, they have different amplitudes. Okay. If we look at the extremes, we're going to have some points here on the left and the right which are fixed. And therefore, these guys are going to have an amplitude of 0. Okay, so in each of our waves that you can see on the screen, you should be able to see that there's some fixed points, and we are going to label them with N. These are N for nodes. A node is a position of 0 displacement in the standing wave. So whilst the rest of the wave, the guitar string in the case of the guitar string, is going up and down, these points are fixed in position, they do not move. And you notice that there's 2 nodes in that top picture, and actually we can use those nodes to measure the wavelength of our wave. You notice there in the top image, this is half a wave, and so therefore the distance from N to N is going to be half of the wavelength lambda over 2. So it's possible to measure that wavelength by just simply measuring the position of the nodes. Look at the bottom picture. Again, we've got some nodes here, and there's 3 of them actually. And again, we can apply that same rule. If we knew where these any of the 2 neighboring nodes were, we would be able to measure the wavelength just by measuring the distance between them. Now you'll have seen just there another letter flashing up, A. Now you notice that in the top picture, we're going to label this middle central point as A, and A stands for an antinode. Now the antinode, as the name suggests, is opposite to a node. It is a position with maximum displacement, or even better, maximum amplitude. All of the points along the wave between the nodes are oscillating up and down, and as we get towards that antinode, our amplitude is increasing, and the maximum of amplitude of that oscillation is at the antinode. So in the case of the guitar string, that's going to be in the center of the string. Again, notice that on the bottom image as well, we've now got 2 antinodes. So it's possible for us to form a stationary wave or a standing wave with 1 antinode, or maybe 2, even 3 or 4. And those are called different modes, and we'll come on to them in a later section. Just for now, just be happy with the idea that these positions have got different amplitudes, and anything in between them is going to behave accordingly. Okay, so what you're expected to be able to do with standing waves, initially anyway, is simply identify nodes, identify antinodes, identify things like wavelengths, etc. Okay, one other point, which I think is covered very, very badly in a lot of the literature, and I think it's really worth taking time to think about, is phase. Now, you should be familiar with the idea of things being in and out of phase. So, for example, in the case of constructive and destructive interference, we have waves in phase and waves meeting out of phase, and that was due to the concept of path difference. Now, you will be expected to know about phase difference in standing or stationary waves, and I think this is quite a tricky concept. However, it doesn't have to be. Let's take the top image here. If we looked at this particular wave here, you'll find that we have 2 nodes, and all of the points lie between 2 nodes. Okay, so if we were to consider 2 random positions here and here, you notice that if we were at the top position here, this point here is at the top, and this point here is also at the maximum. If we then let the oscillation continue, then these points would decrease to 0, go down to negative, and then back up again. And importantly, they would do it together. Okay, and so therefore they are in phase. Every point between 2 adjacent nodes, all of these points along here are oscillating together, if you like, and therefore they are in phase with each other. If they are in phase with each other, this means that they have got 0 phase difference. And this is a common thing that I think students really, really struggle with. Okay, often in progressive waves, we talk about 2 points along this horizontal distance x having different phases. In a stationary wave, standing wave, we do not. They all have the same phase. They're oscillating up and down together. Now, if we look at the bottom picture, what you'll notice is that this antinode, for example, on the left, has a maximum, whereas this one has a minimum. They are therefore going to be oscillating out of phase, or another way of saying is anti-phase. And so this means that their phase difference is the phase difference between points on the left-hand section of the wire of the string and points on the right-hand side of the section are going to be oscillating out of phase. So therefore, the only possible phase differences in our standing wave are 0 or pi. Let's just check that again. All of the points in this left-hand section have got a phase difference of 0, all with each other. All of the points on the right-hand side of this wave have got a phase difference of 0 with each other. However, the points here are out of phase, or pi out of phase, with all of the points here. And so therefore the only possible values of phase difference are 0 or pi. Now I understand I think that's quite a conceptually hard point, so I really do think take some time to think about this. And you'll notice if you try some past paper questions, particularly in the multiple choice, there are many questions which ask you about this, and it's really key that you get this point together. So if you're not sure about phase difference, you're not really kind of clear on what that means, take the time to establish that now, because once you get it and you try it for a few questions, you'll really find that this is a common repeated structure within, as I say, particularly paper 1A, as it's now called. So please go into those questions with some confidence that the answer is either going to be 0 or pi. Okay, I think that's basically it. Okay, again, feel free to pause this video at this point just to sort of take any notes, add anything, copy any diagrams, whatever you need to do. Okay, a reminder of what we've done there. We've looked at what standing waves are. We've understood what is meant by nodes and antinodes, and then we thought about the phase difference and the amplitudes of different points along the standing wave. Hope this has been helpful. If you've got any questions, please feel free to post them in the comments. And if you're ready to, get cracking on with some practice questions, and hopefully the next video, which will be looking at the different forms of waves and the boundary conditions under which they can occur. Thanks for watching.